Hello everybody, this video is about Objective 2D and solving multi-step stoichiometry problems using the ideal gas law. So when we're going from moles to liters of a gas, as you can remember from our stoichiometry unit, if we're at STP, then we're going to use 22.4 liters per mole. And remember, STP stands for standard temperature and pressure, and our standard temperature is 273 Kelvin, and our standard pressure is 1 atm. When our conditions are not at STP, though, we're going to use the ideal gas law to solve these problems. So if we have non-STP conditions, and we're given liters of a gas, we're going to start with the ideal gas law. If we're looking for liters of a gas, we're going to start with a stoichiometry conversion. Okay, so here is example 1. Example 1 and example 2 are going to be a little easier and don't have long drawn out stoichiometry calculations. 3 and 4 will be a little more complicated. So example 1 says, what volume would 20 grams of CO2 occupy at a temperature of 25 degrees Celsius and a pressure of 105 kilopascals? So we're going to start by writing out all of our variables. So we have 20 grams of CO2. Temperature is 25 degrees Celsius. And pressure is 105 kilopascals. And we will need our gas constant. So the first thing we need to do is make sure that all of our variables are in their correct units. So we know temperature always needs to be in Kelvin for our gas law problems. So you need to add 273, so we get 298 Kelvin. Kilopascals, you'll need to convert to ATM, so when you do that, you get 1.04 ATM. And here is where the stoichiometry comes in. We have grams, and N stands for moles, so we need to first convert our grams into moles. So do 20 grams of CO2, and the molar mass is 43.99 grams in 1 mole. So grams cancels out and we have moles, and that gives us 0.455 moles of CO2. So now all of our variables are in their correct units. We're going to plug them into the ideal gas law, which is PV equals nRT. So we have 1.04 ATM. Volume is what we're looking for. 0.455 moles times our gas constant times 298 Kelvin. So when you solve for volume, you should get 10.7 liters of gas. Example number 2 says, what mass of nitrous oxide gas is contained in 20 liters balloon at a pressure of 110 kilopascals and a temperature of 25 degrees Celsius. So we're looking for mass. So using the ideal gas law, we're going to solve for moles, and then we will convert that to grams. So our volume is 20 liters. Pressure is 110 kilopascals, and temperature is 25 degrees Celsius, and then our gas constant. So we need to make sure that all of our variables are in the correct units, so we need to convert kilopascals to ATM. So when you do that, you should get 1.09 ATM. And temperature needs to be in Kelvin, so add 273, and that gives us 298 Kelvin. So we're going to, again, plug all of that into our ideal gas law. So 1.09 ATM times 20 liters equals N times the gas constant times 298 Kelvin. And when you solve for moles, you should get 0.89 moles of nitrous oxide gas. So we're going to convert that to grams. So 1 mole on the bottom of nitrous oxide gas, and the molar mass is 43.99 grams. So moles cancel out, and we have grams. So you should get 39.2 grams of nitrous oxide gas. Example problem number 3 says what volume of CO2 forms from 5.25 grams of CaCO3 at 103 kilopascals and 25 degrees Celsius. So we know we're not at standard temperature and pressure, so we're going to have to use the ideal gas law calculation. So we are given grams of CaCO3, and the problem is asking us to find the volume of CO2 that is formed. So we need to convert that 5.25 grams of CaCO3 to moles of CO2 first before we can plug that into the ideal gas law. So start with 5.25 grams of CaCO3 and convert that to moles of CaCO3. The molar mass is 100.05 grams in 1 mole of CaCO3. And the equation is balanced, so it is 1 mole of CaCO3 to 1 mole of CO2. So when you calculate that, you should get 0.052 moles of CO2. So now we're going to write all of our variables out. Our moles is 0.052. Pressure is 103 kPa. Temperature is 25 degrees Celsius. And of course our gas constant. Okay, so make sure all of your variables are in the correct unit. kPa needs to be converted to atm, and Celsius needs to be converted to Kelvin. So then plug everything into the ideal gas law. 102 atm, volume is what we're looking for, equals 0.052 moles times the gas constant times 298 Kelvin. So when you solve for volume, you should get 1.25 liters of CO2. Example problem number 4 says how many grams of Al2O3 are formed from 15 liters of O2 at 97.3 kPa and 21 degrees Celsius. So we're given liters in this problem and asked to find grams of another compound. So we're going to start with the ideal gas law in this problem. So write out all your variables. Volume is 15 liters. Pressure is 97.3 kPa. Temperature is 21 degrees Celsius. And our gas constant. So again, make sure all of your variables are in the correct units. kPa needs to be converted to atm. So that gives us 0.96 atm. And add 273 to Celsius to get 294 Kelvin. So then plug all of that in to the ideal gas law. So it's 0.96 atm times 15 liters equals N, which is what we're looking for, times the gas constant, times 294 Kelvin. So when you solve for N, you should get 0.597 moles of O2. So now moles of O2 is what we have, and the problem is asking us for how many grams of Al2O3. So we're going to start with that 5.597 moles of O2 and use the mole ratio. We have 3 moles of O2 to every 2 moles of Al2O3. So moles of O2 cancels out, and we want to go from moles of Al2O3 to grams of Al2O3. So 1 mole of Al2O3 on the bottom, and the molar mass is 101.93 grams of Al2O3. So moles of Al2O3 cancels out, and grams is what we're left with. So when you solve for that, you should get 40.6 grams of Al2O3. So you have some practice problems in your packet. Go ahead and give them a try and let me know if you have any questions.